Good morning, everybody. Thank you for joining us today to the AFT webinar session. Today we're going to be webinar is AFT Impulse Pulsation Frequency Analysis PFA module. This is a module that was released on December 2017, and we're going to do our first presentation. My name is Ronaldo Pinto. I'm the Technical Sales Manager for AFT, and I'll be your host today. If during the presentation you have any questions, feel free to type it down in the chat box and the GoToMeeting. And after we conclude the webinar presentation, we'll have a session of questions and answer where I'll be answering all your questions. So today's agenda, we'll have a brief introduction of the module. Then we'll be talking about natural frequencies and resonance, piping system vibration and resonance, PD pump pulsations, and then we'll have a short session of why you should use a PFA module, and then we'll be working an example where we will see the overview of a PFA for Impulse and how it's gonna and how to input and obtain the natural acoustical frequencies of the system and how to model it with the PD bumps. As I said, at the end, we'll have a session of questions and answers that where I'll be answering the questions that you type on the box of the GoToMeeting chat room. So let's start with the introduction. AFT has a pleasure to announce the release of AFT Impulse module for pulsation frequency analysis. As I said, it was released in December 2017. And as you know, acoustical frequency analysis has always been a very well kept secret by specialized companies. PFA will give AFT Impulse user comprehensive access to this technology. Personally, I worked as a pipe stress engineer during 20 years, and when we had to do the layout of a system with the PD pumps, or we would have to contact a company to do the analog study for us, and just hoping that we put the supports correctly. So now you'll be able to analyze the supports with the natural acoustical frequencies and compare them with the mechanical resonance or acoustical resonance. Potential uses for this module: operators, consulting companies, refineries, predictive and preventive maintenance department, AFT Impulse users. So now let's talk a little bit about frequencies and resonance. Every physical system has more than one natural frequencies at which it tends to vibrate or oscillate. It is possible to excite one of the natural frequency of the system. When that happens, the system will experience resonance. In this situation, the system vibration or oscillation will be amplified or grow larger over time. To excite a natural frequency, an external energy source is required. In the case of resonance, the energy source, if the energy source is powerful enough or the system weak enough in a particular matter, the system can exhibit fatigue or excessive plastic deformation. Even if the system does not exhibit fatigue, regular excitation over time of a natural frequency can weaken the system or cause the system to perform in an acceptable way. In mechanical systems, engineers address such issues as changing the stiffness of the system, which is called a mechanical solution, or changing the mass of the system, which is called an acoustical solution. And one of the things you have to determine is which one you have to apply when you have excessive vibration. Piping system vibration and resonance. Piping systems can vibrate or resonance in two ways. Through the pipe solid material, this is called mechanical vibration. If the vibration frequency is at the natural frequency, it is called mechanical resonance. And in this case, you would have a mechanical solution like changing the distance between supports. Or Another type of vibration is through the fluid inside of the pipe. This is called acoustical vibration. If the vibration frequency is at the natural frequency, it is called acoustical resonance. And in this case, you would use an acoustical solution. Causes of piping vibration and resonance. There are many causes of vibration resonance in a piping system. A common cause of acoustical vibration and resonance is caused by positive displacement pumps, also known as PD pumps. PD pump cause pressure and flow pulsation in the piping system. This pulsation can excite any of the natural frequency of the fluid and result in acoustical resonance. Why is acoustical resonance a concern? It is a concern because it can cause vibration. It can cause the piping system to vibrate excessively. This can damage the piping, the joints, or the pipe supports over time. Disrupt the quality of the production of the process. Lead to frequent maintenance, which is costly in terms of labor, materials, and loss of production. So why is PFA module useful? PFA module will allow users to predict and understand resonant frequencies so they can be avoided in operation, ensure that the pressure pulsation amplitudes comply with the API 674 standard, calculate forces generated by pressure pulsation, automatically create scenarios to evaluate the amplitude of the pressure pulsations and magnitude of forces when operating in resonance with any of the acoustical frequencies. So let's start working with PFA and module for AFT Impulse. The process will be divided in 4 steps. The first step is to turn on the pulsation and frequency analysis module. Step 2 is to strike or ring the system. Step 3 is calculate the acoustical frequency and select the frequencies and pump RPMs of interest. And finally, step 4, create a PFA-specific scenario representing the PD pump RPM to determine whether or not you have you comply with 674 standard. So let's talk in detail each one of the steps. Step 1, set up the model. Turn on the pulsation and the frequency analysis module. Select active module from the tools menu and check the PFA pulsation frequency module. Second, select the pulsation frequency analysis from the analysis module menu and check use. This will change the items in the analysis module and will open a new pulsation setup menu. So I'm going to bring the AFT Impulse and do the first step. So the first step, you see this box here right at the left or right corner? Right at the right corner of the program, we have this little box here. You have to activate the module to be able to use it. So you select here and you check the box for PFA pulsation frequency analysis. You hit OK, and then the next step is to go to analysis module, go to pulsation frequency analysis and say use. If you don't select this, it won't use the program. When you activate this module, and with its 2 steps, you will have a new menu that is called the pulsation setup that we will be talking about in the next steps. So now you have to create the module in the model in the step 1. Build a model. This model represents a junction side of the system with 2 PD pumps, G8 and G9 G9 in parallel, fed by a centrifugal pump, G1. We will analyze upper pump, G8. So we have two reciprocating pumps, GH and G9. This is the suction. And we have a centrifugal pump that feeds the system. Okay? So this is the system that we are going to analyze and determine whether or not the natural frequencies and the amplitude of the pressures when the pump operates at a resonant frequency. Step 2, ring the system. A common test for mechanical vibration and natural frequency measurements consists in striking the pipe with a short hammer blow. This is a hammer, it's like a sledgehammer, so it has a rubber head and you hit it, but you can't hit it too hard, because an ideal impact is a perfect impulse which has an infinitely small duration, causing a constant amplitude in the frequency domain. This would result in all the modes of vibration being excited with equal energy. So using this concept, you cannot hit the system too hard. So with PFA simulation, we will replicate this test in a digital mode. We will strike or ring the system with a very short pulse or sudden increase in flow rate. This is our computational hammer. We will observe the natural frequencies of the fluid system. So what we're going to do is we're going to replicate the field test by hitting the inside the pipe with the increment of the fluid in the system. Okay, a short pulse or sudden increase in flow rate, which we're going to apply in the compressor and joint G8. So to apply the rings, we select the pulsation setup from the analysis menu. This is where the ring will be defined. We specify the junction. So we're going to hit it in G8, and the automatic magnitude of the strike will be twice the steady state flow. So here, the program will automatically calculate the strike, and if you want to hit it yourself and determine the strike you want to hit, you would use user specify. But by default, the program will do the test automatically for you. So then, in step 2 on the screen, we have the pulsation source. It is defined right here. So the pulsation source in this case will be a positive displacement pump. Number of head 5s, RPM is 250, and the speed buffer, which is how much you allow the speed to go above 250 RPM, is 12%. So it is a PD pump, then the pump characteristics are entered on the pulsation tab and the PD pump setting tab. And then, generally, the high frequencies of the compressor require major energy. So the ones that we see vibrating in the field are the low frequencies, below generally 100 hertz or 140, below a certain amount of hertz. And the program will calculate that. And so the analysis will be done using a low pass filter to remove these unwanted high frequencies. the PD pump characteristic can dictate the upper limit. So here we have a low pass filter using the method of Chebyshev. Using the PD pump characteristic, the program will calculate, and here it calculates 140 hertz for the maximum frequency that it will calculate it for the low pass filter. And another part of the screen is the step 2. Details of the PD pump are entered in the PD pump setup, used to generate the flow versus time pump curve for the child scenarios. So here we have all the characteristic of the pump. Here, minimum speed is 120 RPMs. The bore is 40 millimeters, stroke 75 millimeters, rod length 360, clearance 70%. Suction pressure is 3,495, discharge pressure, equivalent analog filter, and the phase lag. So I'll bring the program again, and let's go through step 2 again, just to reinforce what we saw. So we go to the pulsation setup. Pulsation setup. It will bring me a screen. So now we have here, we're applying the pulse in the G8 and the junction G8. We'll let the program automatically calculate it for us using twice the steady state flow. We input the pulsation source, which is a PD pump, number of heads 5, pump speed 250, speed buffer 12. If you're doing an analysis and you don't have the characteristic of the pump, of the PD pump, you can use other, and you don't need to do this input. But in this case, we have all the information of the PD pump. So now we're gonna use a low pass filter using a Chebyshev method, and we're gonna use the PDP characteristic to determine the maximum frequency that we need to calculate the acoustical frequency. Finally, in this screen, the last step is to input the PD pump settings. This will allow the program to create scenarios so you can evaluate the compliance with the 674 code. So here we input all the properties of the PD pump, 120 RPM, the bore, the stroke, the road length, the clearance, the suction pressure, the discharge pressure, and the phase lag. So now in step 2, we go and the pipe sections after the pulsation setup is defined. The pulse set frequency will be determined at the maximum steep step, time step, and the minimum number of sections is the controller pipe. The same as impulse, the controlling pipe will be the smallest pipe. Here, the controller pipe will be number 4, okay? And here it does the sectioning for you so he can apply the method characteristic and determine the frequency, acoustical frequencies of the system. So I'll bring the program. Oh, we'll keep continuing, then I'll bring the program. Some pipes can be excluded from the analysis. PD, P8, and P9 are volume elements and not a real pipe. And I'll explain a little bit later, a little bit more later. P10 is an acoustical isolated by the centrifugal pump. So we don't want these pipes to be included in the analysis. So what is this? P9 and P8 are the dampers, or called the bottles. The bottles are, the dampers are low pass filter. And as we know, most of the PD pumps come with dampers because high frequency vibration is very difficult to control. So because you would have to put almost bury the pipe to control the high frequency vibration. So in this case, you filter the high frequency and you let pass the low frequencies. And this is what it is. So these are bottles, as I said, dampers, P9, P8. So you don't want to include an analysis, the same as P2. And finally, we want to exclude from the analysis pipe 10 because this is a centrifugal pump and it isolates acoustically this pipe 10, from the rest of the suction system. So this pipe does not see the acoustical vibration in the whole system because it's isolated by the pump. So here, let's bring the program PFA. We go to analysis and we go to pulsation setup. Sorry. We'll go to analysis and we go to section piping. So it does the sectioning of the pipe. And here is where you exclude those pipes that you, by selecting on the box. We don't want pipe 2, we don't want pipe 8, we don't want pipe 9, and we don't want pipe 10. Pipe 2, pipe 7, and pipe 8 and pipe 9, we don't want it because they're dampers, and we don't want it in the acoustical analysis. And pipe 10, we don't want it because it's isolated. You can add more pipes if you consider they're acoustically isolated from the system, and that way they're not included in the analysis. So finally, in step 2, with everything defined, we can view the flow pulse that will be used to ring the system or the strike. Click Show Pulsation Graph in the lower left corner of the screen. So you select here in Pulsation Graph, and when you select that, it will show you the pulse strike fast Fourier transform of the pulse without filtering, and show the in the first 2 tabs. So here you will see the strike. This is the strike, and okay, the fast Fourier transformer in frequency and volume, and then you will see once the low pass filter is applied, which in this case we saw that it was 140 hertz. In this case, the pulse pipe is now decaying in the sine wave. So here is a low pass filter. This is how it's going to strike. And here is, as you see with the low pass filter, it will decay in 140 hertz. Okay, so let's bring the program. We go to analysis. We go to pipe sectioning, as we saw. This is the part, and we hit pulsation. Show pulsation graph. So here is the pulse that we're going to apply. Totally, it's in gallons per minute. The fast Fourier transformer, low pass filter of the pulse in this case, and here is with the low pass filter at 140 hertz. So once I hit OK, it's going to give me a message telling me that it will apply the pulse right here. It will apply the pulse right here at G8, this is where it's going to apply the pulse to determine the acoustical frequency of the whole suction system, excluding pipe 10 because it's isolated. So I'm going to hit OK. We get the message. The PFA module will now place a forcing function onto the junction you selected in G8 as a transient. So when we hit OK, it will apply it to the system. So now if I go to junction 8, we go to the transient tab, and we'll see a pulsation applied here. So if I tell it to show the graph, it will show us the graph that we saw with the fast Fourier transformer. Okay, so it's applying the system, the pulsation or the strike, so it can determine the acoustical frequency of the suction. So this is what we saw today. Right now, we hit OK after running the model. So now we pass to step 3. After running the model, go to the graph results window. Select the new frequency tab. There's a new frequency tab that will show us the acoustical frequencies. Select the pipe location to analyze and click generate. So here, you select all the pipes that you want to see the acoustical frequency. In this case, we select P4, P5, P6, and P7. So we run the program, hit OK. So now it's going to start calculating the acoustical frequencies. So to recap while it's running, we're hitting it right here in this part, and we're determining all the acoustical frequency of this section of the suction of the PD pumps. Okay, so now that is what it's calculating right now, and the way we stroke it is putting a sudden change of the flow in this in junction G8. So the program is almost done. We go to graph results. So now we have a new tab that's called frequency. And we select, as we said, all the pipes that we want to see the acoustical frequency. So we select pipe 2, pipe 4, pipe 3, pipe 4, pipe 5, pipe 6, pipe 7. You can select more if you want. So when you tell it to generate, it will generate the natural frequencies, and we see all the natural frequencies for all the pipes. If we want to see pipe 7 only or pipe 4 only, we just turn off the rest and see the natural frequency of only pipe 4, and so on. So you can select them all and see them all at the same time, or see one by one. The spikes show the frequencies that excite the system at that location. So as we saw in the graph, we have spikes in this part. So these are the natural frequency that are being excited, and these are the natural frequency for each pipe. The magnitude or how much it is does not tell you whether it's critical or not, because what will be critical is where your PD pump is operating at. Like this small one can be critical, can be if the PD pump operates right here at this frequency. So don't be tricked. Don't the how much it is in the magnitude, how high it is, will not tell you whether it's critical or not. It will the frequency of the RPMs that the pump is going to operate is what it will tell you whether or not you should check that frequency. So now the next step is to select a range of frequency with the largest pressure. Left click and hold while dragging the mouse at the range of selector on the graph. The range selector will determine the maximum value of the selection. When the mouse pulse is released, the frequency where the maximum pressure magnitude is called out using the annotation. So now we select the window in the range of selection. It will select the frequency that requires the lowest energy to be excited. In this case, it selected 35.6 hertz. Okay, it corresponds right to this frequency right here. So this spike. So we right click in the annotations and brings up a menu allowing the user to evaluate this excitation. So now if we right click here in the annotation, it brings another menu where you have the option to convert to annotation or evaluate the frequency. When you select this one here, it will create a tab so you can evaluate when the PD pumps are operating at this frequency and determine or not they comply with 674 or generate the forces if you want to. So let's come in here. So it's interesting. If I try selecting here, it will annotate the frequency right here. If I right click here and I say evaluate, it will bring me a sign telling me that your compressor will not operate it because it's operating between 120 RPMs and so it will not operate at this frequency. So there's no need to evaluate this frequency. So okay, I say okay. So now I'll do it with this one. I'll select the window, and it says the frequency that requires the lowest energy is 35.5 hertz. And if I right click here, it would say, okay, I want to evaluate this frequency. So I said evaluate. So now you will see another window here where I can evaluate, and it has two frequencies. It's 35.5. If your compressor operates at 214 RPM, it will be in acoustical resonance with this one, or at 143 RPM, the same thing. So now we would be ready to evaluate the PD pumps operating at these frequencies. So now here, this is a step with this. A red dot appears. Right here, it tells me the RPMs that it would need to operate. And if I select, if I say create scenarios, it will create the scenarios to evaluate the PD pumps operating at these RPM. PFA process step. Okay. So the table will show the RPMs that will be used to create the scenarios. If we want to deselect, if we select it here, it will show me it would only work with 214. The italicized value are deselected. So here, if you select this here, it will turn it off and it will only evaluate 214. So when we hit create scenarios, it will create the scenarios for us to evaluate the pump operating at these RPM. So let's do it in the program. So we have a red dot, we have it here. We deselect 143 43 RPM. We don't want that. We only want 213. We hit create scenario. So it gives me a message saying this will create one pipe speed scenario with flow rates corresponding to the following pumps, RPM 214. Do you want to continue? And I say yes. So now it created a scenario where it will evaluate the pump, the PD pump operating at 214.7 RPM. So we select this scenario. As you see, these scenarios may have properties since they are dependent. These scenarios have special properties, and it's important for you to know. They are dependent on the configuration of the parent scenario. So these two, the scenarios like 142 RPM and 114 depend on the base scenario. They are read-only, so most of the model cannot be changed. If you want to change it, you have to go to the base scenario. They will be deleted when the parent is changed. If you change the condition of the base scenarios, it will delete this and you will generate another ones to evaluate the operating conditions. They are named with the pump speed and frequency. So the name of the scenarios is the RPMs of the PD pumps and the frequency that it would be in resonance with. The junction where the ring was placed is updated to be a flow versus time profile for the pump running at indicated speed. This is the base of the number of pump heads. So now the pump where the ring was applied, we applied a pulsation flow. Here it is, and this is calculated based on the characteristic of the pumps that you gave initially in the what you specify here in the pulsation setup. So now I'm going to come here. If I go to the workspace and I select junction 8, so now I will see that in this scenario we have a transient, and here we have a pulsation applied that is corresponds to the pump characteristic that you inputted in initially in step 2. So we close here. And we're ready to run the program. When we run this model, there will be several blocks in the step of time to determine when the model reaches the equilibrium. This eliminates any artificial fluctuation caused by a PD pump flow and leaves just the steady state harmonics of the system. The frequency response graph can again be generated. Notice the spike occurs at the frequency of interest. So here we'll see a spike here, and we can evaluate the magnitude of the peak-to-peak pulsation, in this case in PSAD. At the end of the run, the maximum peak-to-peak pressure levels are checked against API 674. So now, as you will see when I see the program, it will check the peak-to-peak pulsation against 674, and the message is pulsation peak-to-peak pressure are within the allowable. So if you operate your PD pump at the frequency of 274, you will have no problems with the pulsation according to API 74. So I'm going to run the scenario at 214. We say okay. So now it's calculating the pulsation. We go to the graph results. We go to the frequency. We say generate. So we see the maximum pulsation is let's see. Let me do something here. So now let's determine the maximum pulsation. The maximum pulsation is if your PD pump operates at 35.5, the maximum pulsation would be 9.82 PSID, peak to peak. So now we go to the output and we go to the pulsation summary. And here, we see that it's checked with API 74 and the pulsation peak to peak pressures are within the allowable. So here's the frequency, and this is the P4, the pipe 4. This is the pipe that has the maximum frequency. If you operate your pump at 274 RPM, the maximum pulsation oscillations, you will see it in pipe 4, which is a dead end pipe, and it's within the allowable. But still, if you want to check it and see the forces that's generated, And in this case, you would go to base scenario. You would go to analysis. You will go to pulsation setup. And you will go for force setup, and you would say, okay, I want to calculate the forces. So now you would say where you want to calculate it. So now I want the difference in pipe 4 and pipe 4. And then you generate the forces. In the scenario, you go to the same procedures and you would have the forces calculated. And that way you can determine whether or not are critical, or you can export it to a pipe stress program like Caesar 2 and calculate the stresses that you would get due to those forces in pulsation, or calculate it in fit for service, API 572. And you would be able to determine whether or not it has fatigue problems, or according to the code. If you have if the level of pulsations exceeds the allowable according to API 74, a warning is given if there are locations that exceed the maximum setup standard, and it will list the locations where the largest DP pumps. So if you have any high pulsations and they don't comply with the code, you will receive a message, and it will tell you that where it is located at. In this case, it's pipe 4, if the pulsation exceeds the allowable. So as you see, it's very easy to use, and I'm sure that it will be very useful when you are using PD pumps, or you just want to do a acoustical analysis, and hopefully you will give it a try. And PFA really is a very useful tool. So now let's go to the questions session of questions and answer, and I'll try to respond any questions that you have. So here we have a question. Based on what you describe, this model does not perform fatigue analysis, and it will be up to the stress engineer's unit. That is correct. The module will calculate only the forces. It will calculate the magnitude of the forces. Remember, impulse is AFT is we analyze flow, so we analyze the perturbance. If you want to do a fatigue analysis, you would have to export the forces to a pipe stress program, and with that, they will be able to calculate fatigue. Like if you're going to use pipe code API 572 fitness for service, you would require a pipe stress program to do the fatigue analysis. But it will calculate the forces for you, and it also calculate whether or not you comply with 674. Okay, so can this module be used to analyze the acoustical induced vibration of release system 2? I will answer this question. Let's start. Okay. Yes, it would be able to analyze the perturbance, but really what you want this module to do is calculate the natural acoustical frequencies. But I'll get back to you with this question, and I'll answer it. So what is next? You will receive a follow-up email with the link to today's recorded webinar and the upcoming webinars. You can download for free from our website and request an evaluation license. If you want to test the PFA and have questions, just you can request an evaluation. The pricing is posted in our website for a USA user, and international, you can contact your local channel partners. Thank you very much for joining us today, and I hope it was useful, the presentation for you. Thank you again, and see you in the next webinar.